Hello, welcome to this quick feedback video on spotting chiral carbons. So to begin the optical isomerism unit, I've set a tutorial which I think most people find okay to follow, and then the quiz tends to throw people a little bit because it is about application of what's in the video, and I've purposely chosen some pretty difficult structures for you to identify chiral carbons in, because then that really tells me if you've got it or not. But it does tend to throw up lots of questions, that quiz. I get a lot of sixth form students asking about how to deduce which carbons are chiral and how you do it in cyclical molecules and things like that. So I'll go through the actual quiz that I set and show where the chiral carbons are and why they are considered to be chiral. Okay, so this is the quiz that I set as part of this tutorial. So you've got the tutorial video which goes through what optical isomerism is all about and what all of these new terms mean. And then question 1 says, what is a racemic mixture? It's a fact recall question, so it's mentioned in the video and you just need to learn it as a definition really, that a racemic mixture is a 50-50 mixture of opposite enantiomers. So enantiomers is the term that we give to optical isomers that are the mirror image of each other, non-superimposable mirror image of each other. So if you've got both mirror images and you've got the same amount of each mixed together, we call it a racemic mixture, or we can also call it a racemate. Racemate, there we go. Okay, so quick fact recall question, that one's not too bad. Then we've got compound A, and it asks how many chiral carbons are there in compound A. So a chiral carbon is one that is attached to 4 other groups. Now, if I do something like this, so here we've got a carbon atom that's attached to a hydrogen, a chlorine, a fluorine and a bromine. It's really, really easy to say then that that carbon there is chiral, and we tend to denote it with a little star. It's dead easy to see that it's 4 different groups that are attached. So if I give you a slightly different example, if we take that hydrogen away and we take the chlorine away, and this time we give it a double bonded oxygen, immediately I can say that this is not going to be a chiral carbon, because any carbon that has a double bond coming off it cannot have 4 different groups attached. It can only have 3 different groups attached maximum if it's got a double bond coming off it. So that one is dead simple to say it's not chiral because it's got a double bond on it. So it's not 4 different groups. Then it gets a little bit more complicated, because we could put a hydrogen, a bromine, a carbon and a carbon. Now, immediately looking at that, I know that's only part of a compound, because obviously we've got to have things coming off here and things coming off here to complete the structure. But lots of people would look at that and say that can't be chiral because this is a carbon and this is a carbon. But the idea of chirality is bigger than that. It's the whole molecule that matters. So it's about symmetry across everything. Now, if this was a methyl group and this was a methyl group, then you'd be correct in saying that that central carbon is not chiral, because that group is identical to that group. But what you can do is, this could be an ethyl group instead. So it could be a bit bigger. Now, that carbon in the centre, that is chiral, because coming off that carbon we've got hydrogen, a methyl, an ethyl and a bromine. All 4 of those groups are different, despite the fact that coming straight off the bond we've got carbons in 2 directions. So there are some examples of linear compounds. So we're not going to do cyclic ones just yet, because they do get even more complicated in terms of symmetry. But let's have a look at some linear ones first. Now, I've made this even more complicated by giving you skeletal formula, so you've got to figure out where the 4 different bonds coming off each carbon are, and whether they're going to carbons or whether they're going to hydrogens. So I'm going to add a little bit of detail onto this diagram. So starting from the bottom, we've got this OH alcohol group here. So this bond is going to an oxygen, and this is a carbon. we know that this is a carbon, this is a carbon, and this is a carbon. So these are carbon atoms that are all, they're shown as joints within a skeletal formula because we don't actually draw the letter C out. But we're missing some bonds as well, so let's add some bonds on. So starting at the bottom again, we're going to an OH group in one direction, the rest of the chain pointing up, which means we must have, we must have two other bonds coming off here. And because it doesn't say what's on the end, it has to be a hydrogen. Moving up to this next carbon along the chain, we've got an alcohol group pointing off this direction. We've got the rest of the chain going down, the rest of the chain going up, which means we're missing a bond. This one's only making 3 bonds, so we need to draw in another bond as well. So we draw a bond here, and it has to be a hydrogen because we haven't said what's coming off it. This carbon here has the rest of the chain to the right, the rest of the chain to the left. It has an alcohol group, which means we're missing a bond, so we'll draw in another bond with a hydrogen on the end. And then the final carbon, we have got 2 bonds going this way and 1 bond going that way, which means we're missing 1 bond, which must have a hydrogen on it. So that's more like what the full structure looks like. So I'll draw this out, not skeletal, next to it so that you can see, without all the mess everywhere, what it actually looks like. Okay, so there's the full displayed formula of the structure that's on the left. So now we just need to look at each of these carbons and decide whether or not they're chiral. So first of all, I'll highlight them so that we can see where the carbon atoms are easily, and then we'll decide whether or not they've got 4 different groups coming off. Right, so here's our carbon atoms. So again, we'll start at the bottom. So we're looking at this carbon here. In one direction, we've got an alcohol group. In another direction, we've got a hydrogen. Then we've got another hydrogen. So straight away, these 2 groups are the same. So this one cannot be chiral. Next one up has an alcohol group and a hydrogen sticking off, so that's good. Then it goes to 2 carbons, but let's look a little bit further than that. In this direction, this carbon has 2 H's and an alcohol, but this carbon has 1 H, an alcohol, and another bit of a carbon chain. That means that this entire portion of the molecule here is not identical to this portion of the molecule here. So if you're looking around this carbon in particular, you've got to look at everything that comes off in 4 directions, which is these 2 huge chunks, and they can't be the same. They're not the same, so we've got 1, 2, 3, 4 different groups coming off this carbon. That makes this carbon chiral. Okay, your third carbon along, which is this one, has an H and an OH, which is great. They're 2 different groups. Then it's got this bit, which is an aldehyde end, which is a 3rd different group. And this isn't a hydrogen, it isn't an alcohol, and it isn't an aldehyde group. It's a carbon with a hydrogen, an alcohol, and the rest of a carbon chain going down to another alcohol down here. So this entire portion of the molecule here is not identical to this portion of the molecule here, which means the 2 things coming off these bonds are not the same as each other. So that's 4 different groups. That makes that carbon there also chiral. And finally, we've got this carbon here, and we need 4 different groups attached. But as you can see, it's got a double bond, which means there's actually only 3 different groups coming off this carbon. So straight away, it cannot be chiral. Okay. So that's how you do that one. That one's got 2 chiral carbons, and we've identified those with a little star. Right, we'll move on to question 3. Okay, so that's compound A. Here we've got compound B, and question 3 is going to ask us how many chiral carbons are there in compound B. Again, it's skeletal, so we need to add a little bit more detail and identify where the carbons are. So we'll do this one a little bit quicker. I'm going to highlight the carbons with my yellow highlighter again. So we have got one here, and that's the only one that's actually got a C on it. But we know because it's skeletal, there'll also be a carbon here, one here, anywhere where there's joints in the structure that haven't got a letter on them. So there are our carbons, 1, 2, 3, 4, 5, 6 carbons in that compound. We need to decide whether each of them is chiral. We also need to make sure that any extra bonds that should be there are there. So this carbon here is going to an H, an H, and an OH. That's what this bit tells us. And it's coming down to the rest of the molecule, so that's making 4 bonds. This one is going up to that carbon, down to that carbon, and across to that oxygen, which means it does have another bond going to a hydrogen. If we go around clockwise, we go to this carbon here, which is going to an alcohol group pointing down, a carbon going down to the left, an oxygen going up to the right, which means it does have another bond with a hydrogen here. Bottom right carbon goes down to an alcohol, goes across to a carbon, across to another carbon, which means it must also have a bond to a hydrogen there. The bottom left carbon goes up to an alcohol group, left to a carbon, right to a carbon, which means it must have a hydrogen coming off here. And the final one on the left-hand side goes down to an alcohol, up to a carbon, down to a carbon, so it's got a hydrogen here. So now that we can actually see the 4 bonds for each of these carbons, it makes it a bit easier to decide whether or not we've got something that's chiral. So let's start with this one that's actually got a C in it. The CH2OH means it goes off to a hydrogen, and an alcohol. Well, if it goes off to 2 hydrogens, it can't be chiral, so this one's not chiral carbon. So just because it's cyclic and I'm going to get confused, I'll put a little cross through that one so that we know it's not chiral. Let's go down the molecule to this one. This one goes across to an oxygen, down to a carbon, across to a hydrogen, and up to a carbon. So it depends if this carbon and this carbon are symmetrical, are identical to each other. Well, straight away I can say that this carbon is part of a ring and this carbon isn't, so they're not going to be the same as each other. You can also look at it as this carbon has 2 hydrogens coming off it, whereas this carbon only has 1 hydrogen coming off it. So this and this, they're not the same. So here we've got an H, an O, one different group and another different group, so that one's got to be chiral. So we'll put a little star there. Going around clockwise, let's have a look at this one. This one goes to an oxygen, a hydrogen, an alcohol, and that oxygen's not an alcohol, so they're 2 different groups. So an oxygen, a hydrogen, an alcohol, and a carbon. Straight away, that one's chiral because it's got 4 different groups. Okay, next one down. This one goes to an alcohol and a hydrogen, 2 different groups. Then it goes to this carbon and to this carbon. Well, is that carbon and all of this part of the molecule the same as this carbon and all the rest of the molecule? It's dead easy to see that they're not the same, because if we go in this direction, we go carbon, oxygen. And if we go in this direction, we go carbon, alcohol, or carbon, carbon. So going in that direction and going in that direction takes you to 2 different sets of atoms arranged differently in space. So this one has got 4 different groups attached, so it's chiral. This one here goes to a hydrogen and an alcohol group, which are 2 different groups. Then it goes to a carbon and it goes to another carbon. So are those 2 carbons in different positions? Well, if you go to the right, you go to a carbon with an alcohol. And if you go to the left, you go to a carbon with an alcohol. So the same so far. So let's go further round. If you go to the right, you go to the carbon with the alcohol and then onto a carbon with an alcohol. Whereas if you go to the left, you go to a carbon with an alcohol and onto a carbon with this chunky chain coming off it as well. So they're not the same. They're not symmetrical around this carbon, so this carbon has to be chiral because it's got 4 different groups attached. And we've got one more. So this one here, we go to a hydrogen and an alcohol, which are 2 different groups. Then here we go to a carbon and here we go to a carbon. So are these 2 different groups altogether? Well, this one is a carbon with a CH2OH group, and this one is a carbon with just an OH group. So they're not the same. When you go in that direction and that direction, you come to 2 different sets of atoms. So that's 4 different groups attached. That means that that one is chiral, which means that altogether in this molecule, you have 5 chiral carbons, and they're denoted with little red stars. So I'm hoping this is making a little bit more sense to you now. It's the idea that it's not just that goes to a carbon, that goes to a carbon. But what are those carbons joined to? It has to be the entire chunk of the molecule that you're looking at. And it is more difficult with something cyclic. But, I mean, this cyclic molecule's handy because it's got this oxygen and it's got this bit, which makes it very unsymmetrical anyway. So the chances are you've got a few chiral carbons in there. Okay, so that was question 3. So we move on and have a look at the next one. Okay, so how many chiral carbons in compound B? And now we've got this absolute horror of a question. Compound C, you need to look for chiral carbons in this absolute mess. Now, one of the clues I have pointed out to you is that if you've got bonds that are wedged or dashed, so you're trying to show 3D structure, like this wedged bond here, and this dashed bond here, wedges here, chances are that the carbon that they're coming from is going to be chiral. Otherwise, they wouldn't be trying to represent it in 3 dimensions because it wouldn't matter. Optical isomerism is only there because these molecules are 3D, and that's why they're non-superimposable mirror images. So there's a lot of clues here that these ones are going to be chiral. So let's go through those first. So where do we start? Let's start from this end of the chain and work our way around. So this has got 3 hydrogens coming off it, so it's not going to be chiral. This one's got a double bond, so it's not going to be chiral. This one's not a carbon. There's our first carbon here. And we've got a wedged bond, which tells us it almost certainly is chiral. And we know it is because it goes to an oxygen and a hydrogen in these 2 directions. The hydrogen you can't see because it's skeletal. And then here it goes to this carbon, which goes onto a double bond, and this carbon, which goes onto a carbonyl. So that one there is chiral. So we can stick a little star there. Let's go this way. So this one's got a double bond on it, so it can't be chiral because it can't have 4 different groups attached. This one has got a wedged bond, it's likely to be chiral. So it goes to a carbon with an alcohol, a methyl group, a carbon with a carbonyl, and a carbon that goes off to a hydrogen and 2 other bits of the chain. So that's got 4 different groups attached. So we can give that one a little star. This one also has 4 different groups attached, and it's wedged anyway, so you can probably tell it's 3D. So we've got an alcohol group. We've got hydrogen that we can't see because it's not drawn in, so there's 2 different groups. Then this one goes to 2 hydrogens, whereas this one goes to 4 different carbons. So that carbon and that carbon aren't the same. So this here must be chiral. Honestly, if all else fails, pick the ones that have got the wedged and dashed bonds, because I've never seen an example where it draws wedged and dashed bonds and isn't actually chiral in these sort of questions, at least. Okay, so moving around, we've got this carbon here, but that goes to 2 hydrogens, so that's not 4 different groups. Then we've got this one, which is going to be chiral. We know it's because it's wedged. So we've got it going to an oxygen, to a hydrogen, to this carbon, which has got carbons and oxygens around it, and this carbon, which has got 2 hydrogens around it. So that one's got 4 different groups. So give that one a star. This is going to be the biggest bit of the video, I think, going around this molecule. Right, that's an oxygen, so that doesn't matter. That's a carbon, but it's got 2 different, it's got 2 hydrogens coming off, which are the same, so that one's not going to be chiral. But this one's likely to be, because it's got this 3-dimensional structure around it. So this one goes to an oxygen that's part of an ester. It goes to a carbon that's linked to a single bonded oxygen, so there's 2 different groups. It goes to a carbon that is also linked to a single bonded oxygen, but only through 1 bond and not through 2. Doesn't go around this bend, so it's not the same. And this carbon, which has got carbons all around it, and then this hydrogen. So that one there is going to be chiral. Okay. This one. This one's got 3D structure, so it's likely to be chiral. It's got hydrogen. It's got a carbon, which goes to a methyl group. It's got a carbon, which goes to an oxygen, which is part of this big chunk, and we haven't got another one of those, so that's going to be a group on its own. And we've got a carbon that goes to this weird square with the oxygen in it, and we don't have that anywhere else. So that is 4 different groups. So that one's chiral. Okay. If we just take this little detour down to this corner, just to make sure there's nothing going on here, That's an oxygen, that's fine. That's a carbon, but it's got a double bonded oxygen, and that's a carbon, but it's got 3 hydrogens. So these two don't have 4 different groups attached, so they're not chiral. So we can come back up and we go to this carbon here. This one's got 3D structure, likely to be chiral, so it goes to an oxygen, which is part of this aromatic ester group. It goes to a carbon, which has an alcohol group coming off it. It goes to a hydrogen, which we can't see because it's not drawn in. And it goes to a carbon, which has a carbon, and a hydrogen coming off it, which isn't the same as anywhere else. So that one's chiral. Okay. We will drop down and have a look here. That one's got a double bond, can't be chiral. This one's got a double bond, can't be chiral. And each of these carbons... I mean, benzene is very, very symmetrical anyway, so there's not going to be any chirality in something that's very symmetrical like that. But they've all got double bonds anyway, so they can't have 4 different groups coming off. So we'll go back up to here. This one's going to be chiral, it's got a wedged bond. So it goes to an alcohol. Then it goes off in a straight chain over this way towards an oxygen. And then this way it goes around a cycle. Now, if this cycle was completely symmetrical, then this carbon wouldn't be chiral. But it's not symmetrical because you go 1 bond, 2 bond, and then you've got a double bond. This way you go 1 bond, 2 bond, 3 bond before you hit the double bond. So straight away that's not symmetrical. There's loads of things that make it not symmetrical, but that's just one example. So going that way and going that way doesn't take you to the same atoms. That's an alcohol and that's a straight chain, not a cycle. So, well, kind of is a cycle, it's this cycle, but you can see it once you practice enough, you can start to see that they're just not symmetrical, they're just not the same as each other. So that one is chiral. From here we'll go up. This one has got 2 methyl groups, so it can't be chiral. This one's got 3 hydrogens. That one's got 3 hydrogens, so they can't be chiral. And then we get to this one here, which has got a double bond, so that one can't be chiral. This one's also got a double bond, so that one can't be chiral. That's a methyl group, so it's got 3 hydrogens, so that can't be chiral. Then we get to here, which probably is going to be chiral because it's got this 3D structure. It goes single bond onto a double bond. It goes single bond carbon with 2 hydrogens. It goes oxygen, and it goes hydrogen, which we can't see, so that's 4 different groups. That one's chiral. Let's just finish this little loop off because we've got this one here, which we haven't looked at. This is a CH2 group. It's got 2 hydrogens that you can't see. 2 of the same group means it can't be chiral. So that's all of this part of the molecule considered. Let's move over to here. That's an oxygen. That's a carbon, but it's got a double bond, so that can't be chiral. That's a carbon, but it's likely to be chiral because it's got this structure here. It goes alcohol, ester, amine sort of group, and hydrogen. So that one's chiral. This one's going to be chiral because it's got this. So it's got a benzene ring, a hydrogen we can't see, an amine sort of group, and then all of this rest of the molecule. So that one's chiral. As we said before, benzene's not going to be chiral because whether you consider these to be double bonds or not, these aren't making 4 bonds. These carbons are only making 3, so you can't have 4 different groups attached on any of those, so they're not chiral. So now we go up here. That's a nitrogen. That's a carbon, but it's got a double bond, so that's not chiral. And we're back onto another benzene ring, which none of those carbons can have 4 different groups attached to them, so they can't be chiral. And that's it. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 chiral carbons in that compound. It's an absolute nightmare to look at, but if you follow it systematically like that and you look at what's attached to each of those carbons in turn and you don't get confused by its skeletal nature, make sure that you know where the carbons actually are because they're not written in, it's the same as any other molecule. So if you could do compound C, or if you can do it now, then I think you pretty much understand what we're doing here, because that's an absolutely nasty one. But the rules are all the same, so hopefully that helps. Let's see if we've got any more questions. How many in compound C? We've done that. Describe how you would distinguish between separate samples of two optical isomers. Right. If you see in an exam question, distinguish optical isomers, you're looking for plane polarized light being rotated in opposite directions, and that's it. So if you've got two optical isomers and you want to make sure that they're different to each other, you want to know which one's which, you shine plane polarized light through them, and one will rotate it in one direction and one will rotate it in the other direction. And beyond that, you don't need to know anything after that. You don't need to know what you would use. You don't need to know what a polarimeter looks like. You just need to know that you would shine this light through, and one would rotate it one way and one would rotate it the other way. There we go, so that's it. Shine plane polarised light through the samples, one rotates it one direction, one rotates it in the other direction. Question 6 asks which one of the following can exhibit both geometrical and optical isomerism. So for this question, I need you to remember what geometrical isomerism is as well as optical isomerism. And to help us understand this question, because this is a real past exam question, multiple choice question, I'm going to draw these out in full displayed formula for you. Okay, so I've drawn them out, not quite full displayed, because it quickly became apparent that I wouldn't have any space. But I've drawn them out and I've alternated the colours so that we're not seeing one big structure all muddled up. And then we'll have a little look at the question. So it asks which can exhibit both geometrical and optical isomerism. So geometrical isomerism, you need to remember, is the one where if you've got a double bond, you could have the highest priority groups being on the same side, like that. And if they're on the same side, they're called Z isomers, so I'll just call those two groups Z. Or on opposite sides, which is an A isomer, so you'd have your highest priority groups there and there. So that's your geometrical isomerism. Now, one of the dead simple rules for figuring out if something's going to exhibit geometrical isomerism is that you wouldn't have, let's just get rid of that. If you've got something with a double bond and you've got the same thing here and here, then that will not exhibit geometrical isomerism, because basically it doesn't matter if you flip those round, you still won't end up with two different molecules. They'll be exactly the same molecule as they were before, because these are the same group. So if you look at one of your carbons of your double bond, if they have the same group attached, they're not going to exhibit geometrical isomerism. You can't get E and Z. Now, you can have a good think on that yourself if you slow down and draw each of these out and think about why that's the case. But if we use that as a rule for now, then we can discount some of these straight away, basically. Okay, so we're going to start with the geometrical and have a look for that. So let's have a look at where the double bond is and determine whether or not these can exhibit geometrical isomerism. Well, the top one has a methyl group and a methyl group, so that can't exhibit geometrical isomerism. So straight away, we can say that that's not the answer, because it doesn't matter whether it exhibits optical isomerism or not. It doesn't exhibit geometrical isomerism. Right, the next one, if you look here, that group and that group are different. And here, that group and that group are different. So that one can exhibit geometrical isomerism. So we could be looking at that one. Okay. C, if we look at the double bond, here we've got a methyl and a methyl. These are the same. Doesn't matter if you switch those around, you will never get an E and a Z form of this particular compound, because you've got the two same groups here. So this one does not exhibit geometrical isomerism, so it can't be that one. And the bottom one, here's your double bond. Well, here you've got hydrogen and a hydrogen. You can switch those around all you like. You're not going to get geometrical isomers, so it can't be that one. So actually, if you'd have started looking for optical isomerism first, you could have spent quite a long time thinking about this question. But if you look for the ones that can do geometrical first, you get your answer without even worrying about optical isomerism, because we know it can't be that one, we know it can't be that one, and we know it can't be that one. So your answer has to be B. Just to double check, we'll make sure that it does exhibit optical isomerism as well. Otherwise, the question's probably wrong. So let's take that away. and we don't care about geometrical anymore, we've done that. So let's have a look at optical. So we're looking for a chiral carbon, it's got 4 different groups attached. So let's start here. This carbon, oh, didn't mean to do that. This carbon here has 3 hydrogens, they're all the same, can't be chiral. This carbon here has 2 hydrogens, both the same, so it can't be chiral. This carbon has a double bond, so it can't have 4 different groups attached. This carbon also has a double bond, so it can't have 4 different groups attached. This carbon has a carbon, which is an alkene, a hydrogen, a methyl, and an ethyl. So that one is chiral. Let's just put a little star by that and then double check the rest. Doesn't matter anyway because we've got our answer now, but just for complete sake. This one has 2 hydrogens, so that can't be chiral, and that one has 3 hydrogens, so that can't be chiral. That's your chiral carbon, and these 4 groups coming off the alkene give it geometrical isomerism as well. So your answer is B. And that is the whole quiz. Hopefully that explains a little bit about how to spot chiral carbons. If I just whiz back up for a moment to one of the ones that had some cycles in it. The other question that I get a lot is about how to determine where chiral carbons are if something's cyclic. So what you just need to bear in mind is, for example, on, let's get a highlighter. On this cycle here, if we just pick this one out, if you're looking at a carbon that's in there and you want to know if it's chiral, what you need to be doing, so this carbon here, for example, is you need to be looking in both directions. So these 2 are fine. I mean, that's one group and that's another group. You can see that straight away. But it's whether this one and this one are the same. So you just need to follow the cycle round. So if you go up, you come to one with 2 methyl groups. Whereas if you go that way, you come to one with 2 hydrogens. And you just follow it around both ways. And as soon as you come to something that's different, it makes it unsymmetrical. And that means that you're going to have something that's chiral if these 2 groups are also different. I hope that helps. If it doesn't, drop me a comment. If it does, drop me a comment. Let me know whether or not you think you understand it, and you can have some more practice on this when we come back to organic chemistry after you've done a bit of physical. So thanks for watching.